All right, I think we can start this webinar now. First of all, a warm welcome to everyone who joined. My name is CNC銑削, and I will be your host today. Apart from being your host, I'm also one of the customer support engineers at Diabetics. So basically that means if you have any questions regarding the software, I will be most likely your primary contact. As a student, I did my master's thesis on topology optimization at the KU Leuven. So it's not a surprise that I started working at Diabetics. All right, I can see a couple of familiar names in the attendees list. So yeah, I'm very happy to see you again. And I can also, of course, see some new names. So of course, very welcome to those new people as well. For today's webinar, I prepared the following topic. Where we will explore 3 different manufacturing techniques and how they impact basically the most optimal cooling solution for a power inverter. All right. So for today's webinar, I will cover the following topics. So introduction that we already did, of course. Right after this, I will then look into 3D printing, die casting, and CNC milling in more detail. Explain a bit more on where each of those manufacturing techniques can be used, or where they have their strengths and their weaknesses. We'll then apply those manufacturing techniques on a single application, so a double-sided inverter. I'll explain it a bit on slides and as well on the software. Afterwards, we'll have a Q&A session, so if you have any questions, feel free to put them in the chat box. Our moderators will follow the webinar, will already answer those questions, and at the end, if I see any unanswered questions or very interesting topics, then I will cover that in the Q&A portion of the webinar. And then we'll end by basically letting you know how you can try ColdStream for your own. It's quite a jam-packed program, so let's try to keep everything in the 30-minute marker. But let's start with the beginning, the manufacturing techniques. So as the title of this webinar implies, we'll be covering 3D printing, die casting, and CNC milling. When we mean 3D printing, we mean in general additive manufacturing. So it can be SLM, SLS, LPBF. So all additive manufacturing techniques fall within that 3D printing category. With additive manufacturing, you have the potential to design very complicated and very organic 3-dimensional objects, which of course have a big, as a benefit of a big design freedom. With die casting, the main principle behind it is that you spend quite a bit of money on a mold, but that you reuse, or a couple of molds, that you reuse those molds to manufacture or to make those components. So basically, let's say you have you want to die cast with metal, you pour a liquid metal inside of that mold, it then solidifies again, and once it's all solid, you can take it out of the mold and reuse that mold. So it's very well used, or it's very applicable for high volume production. And then we have CNC milling, where I'm very sure you all saw at least one video online already, where you start from a fully solid block of material, and a tool will start chipping away at the block to get to the final solution. All right, so what are the main strengths and the limitations of each of those manufacturing techniques? As I already covered in the previous slide, die casting is more applicable for mass manufacturing, so we have a high volume, or where you need to make a high volume of components, because the molds themselves are quite expensive to make. If you go all the way to the lower end, CNC milling and 3D printing are most commonly used for lower volumes, for instance prototyping, where basically you don't have to invest in a mold. You just send this geometry to either the milling machine or the 3D printing machine, and those machines will make the components. All right, and then what are the design flexibilities, or what is the design flexibility of each of those manufacturing techniques? With 3D printing and CNC milling, the machines quite easily adapt to those new geometries. So the design flexibility is of course very high. with 3D printing, the structures can be very organic, can be very 3D-like even. So the design flexibility of 3D printing is much higher compared to CNC milling, especially if you only have single-axis CNC milling. While with die casting, you're stuck with the mold that you made. So if you want to make a small modification to your design, then you have to make a new mold. So the design flexibility of die casting is quite limited. All right, that's everything that I wanted to cover about the manufacturing techniques. We'll now apply them on a double-sided power inverter. What does the application look like? So we have two heat sources, one on the top and one on the bottom, and in between we have a heatsink sandwich. The heatsink itself contains a housing to contain the fluid, and then the fluid, of course, within it, going from in to outlet. And then beneath the heat sources, we specify a design domain that will become a bit more clear later on. Only within the design domain can we then create optimization structures. All right, so how can you tackle this problem now? You can go with the conventional way of working, which I'm very sure most of you will be very familiar with, where you start with a CAD model, do a CFD simulation or physical experiments, post-process the results, analyze what needs to be changed, and loop through this until you get a solution. The amount of iterations that are needed, of course, very much depends on the time that you have and on the expertise of the designer. What you can also do is completely break away from this design cycle by using generative design software like ColdStream, where you basically upload your geometry, you fill in some data. I'll get back to that in the next slide. And then ColdStream will fully autonomously cycle through hundreds and hundreds of designs, making small modifications each time to get to the best possible solution for your application. And it can look something like this. Yes. So what does the workflow look like on ColdStream? So as I mentioned, you have to upload your geometry, of course. So ColdStream will adapt to whatever you upload. And then you have to follow these three steps. In the first step, you have to define the solid the fluids. So is it will copper be used? Will aluminum be used? Or is it made out of plastic? And for the fluids, will it be air cooled, liquid cooled? And if it's liquid cooled, will it be water glycol, or something else? Then you have to define the barren conditions. Is it natural convection cooled? Is it forced convection cooled? What does my heat load look like? That's something that you specify in step 2. And then step 3, which is a bit of a new one compared to more traditional CFD software, we have to define a design domain. As explained a few slides earlier, we already defined the design domain below the heat sources. And where you have to set the targets. And the targets that let ColdStream know what to optimize for. Maximize heat exchange efficiency, constrain the pressure drop, minimize the weight. What else can you do? We have 20 plus targets that you can mix and match however you see fit. And that's basically it. So once you completed all these steps, you can then submit the case. ColdStream will then fully autonomously cycle through hundreds and hundreds of designs. And once ColdStream is ready, you will be able to download the optimized geometry in step file format. Okay, I think I've talked about, I've used the slides enough for now. So I will switch to the software. Yes. All right, so this is ColdStream, or at least the main landing page after you log on to ColdStream, and as the project overview. As the name implies, it gives an overview of all the different projects to keep everything as organized as possible. All right, for this webinar, I will scroll down and navigate to this project folder. Yes. So inside your project folder, you then have your different cases that you want to solve. And with cases, I mean the engineering problems that you want to solve. We have 3 types of cases on ColdStream: custom design, simulation, and we don't have it here, but we also have the standard design mode available. So with simulation, that means, for instance, you already have a design and just want to do a quick CFD simulation to know the performance of that existing design. You can run a CFD simulation. With custom design, as the name implies, ColdStream will design a fully custom design to your application. using any of the manufacturing techniques that we will cover later today, while standard design, that's more of a parametric optimization of pins and fins. All right, so once you create a new case, you then have to upload your geometry. I will not bore you with that. It's simply clicking on a step file and uploading that. I will go straight to a case that already contains a geometry. Yes. So inside of your case, you can then see, or once you upload it, your geometry, you can then play around with the geometry in 3D and see all the entities that I've uploaded in my regions tree with all the relevant dependencies. So I have two parent regions, as we call them, a liquid and a housing. Inside of my liquid, I have a design subregion, so that's a volume, additional volume that fully overlaps with my coolant. And then if you see these symbols, that represents boundary conditions. And the only thing left for ColdStream to do then is fill in the relevant information. So let's start with step 1, defining the solids and the fluids. So the coolant is of course of type fluid, so I will select fluid. And then you have to let ColdStream know what material will be used. Will it be air cooled? Will it be water cooled? You can simply search for it. Is it temperature dependent, temperature independent? You can simply search for that. Or if you want, you can create your own custom materials by filling in the relevant information, of course. But here we'll use water glycol with a 50-50 mixture with fixed temperature properties as the heat source. Or the heat source is not that big, so we don't expect too big of a temperature rise between in and outlet. And then the additional physics settings at the bottom we'll leave as standard. So we won't include buoyancy. We'll use the K omega SST terminals model. We exclude radiation, and we don't want any volumetric heat source inside of our coolant. Then we have the housing surrounding everything, which is of course a solid made out of aluminum. And again, we'll keep all the other physics settings disabled, so no radiation, no volumetric heat source, and no rotation. Our heat sources themselves, we simplified it here a bit. We could have taken the full PCB models or the full chips and heat preparators combinations as their own regions, but to simplify it a bit, we just assumed that all the heat, we basically only introduced the heat at the interfaces. So we assign them as boundary conditions, and from the dropdown we can then select what type of boundary condition we want to use. In most cases, we want to specify a heat flux, so that's why when we can specify a heated wall boundary condition. And yeah, both sides produce 150 watts, so we'll put the 150 watts in that in that input field, and that's exactly the same for the bottom heat source as well. I'll come back to the targets later. All right, so that's the boundary conditions for the housing. Then we can set the boundary conditions for the coolant. The inlet is on the left and the outlet is on the right. And again, from the drop-down, you can then select what type of boundary condition you want to use. Do you want to optimize for a given inlet condition? You can use a fixed flow rate inlet condition. Do you want to optimize for a given pressure between in and outlet? You can set the pressure inlet condition. Or if you already know what the pump or the pump or the fan, sorry, is, you can specify a pump or a fan inlet condition. But here it's a fixed flow rate inlet, where we specify the mass flow rate to be just below or just above 0.04 kilograms per second, and an inlet temperature of, if my math serves me right, 45 degrees Celsius. What comes in must go out, so again we can select from the drop down what type of outlet condition we want to use. Usually with the fixed flow rate inlet, the pressure outlet condition is most commonly used, but you can also put a fan outlet or a pump outlet if you want to have the sucking effect rather than the blowing effect. All right, so that's the solids and fluids, and that's the boundary conditions. Now we can set the design domain. And the design domain, as I mentioned earlier, that's an additional geometry that you define your CAD tool that fully overlaps with, in this case, the coolant geometry. You can then specify out of how it will be manufactured. So will be CNC milled, 3D printed, die casted, sheet metal formed, or is it an electric wire that you want to generate? In this webinar, we'll only consider the top 3, and we'll, at the moment, consider die casting. So once you've selected die casting manufacturing technique, you can then select the material or the the settings that govern die casting. So you can either select one of the predefined settings, or you can create your own custom settings by filling in the relevant information. These parameters will be a bit alien to you if it is the first time that you see ColdStream. So I will quickly explain what those manufacturing techniques mean. So if we go to die casting, we can then immediately see what type of structures that we can expect from die casting, and how the input parameters change, or how the input parameters affect those structures. So RF min and RF max, that specifies the minimal and maximal width of the structures. BRI and BRO are respectively the fillet angles at the root and the tips. Angle is release angle. To get it, the bigger the angle, the easier it is to get out of the mold. The smaller, the more difficult it is. Delta is the height of the design domain, of course. And then orientation is in what direction these structures will be formed. All right, so that's what those parameters mean. And in this particular example, yes, I will search for 2. Yes. So we specify that the minimal structure width at the root needs to be just above 6.1 millimeters. We don't want to put a maximum constraint, so we put a very high value. The bending radii at the tip and the root are quite small, so it's only 1 mm. The release angle is also very small, 2 degrees. And the delta, so the structures are 3 centimeters high. All right, and now for orientation, we specify the y-axis, so the structures will be formed in this direction. And the structures are made out of aluminum, so it will be aluminum that will be casted. All right, so that's the design domain for die casting. Next we have to let ColdStream know what to optimize for, and that's where the targets come in. So in this particular example, we solely want to consider the temperature minimization objective on both heat sources. And as the name implies, it tries to get the temperatures down as much as possible. And both targets are equally important, which is why the weight is equal, here, equal to 1. Next, seeing as we optimize for a given flow rate, we don't want the pressure drop to rise to something irrealistically high. So we put a pressure loss constraint to, this is wrong, 400 Pascal. So to make sure that we don't fully fill the design with solid material. All right, so that's it. Once all that information has been filled in, I can then submit the case and let ColdStream do the heavy lifting. But as I mentioned, we also want to look at other manufacturing techniques. So we let the case run 4 times in total, twice with die casting. So we already covered the die casting for this, the settings for this case. So, where we also had a look at what would change if the release angle is 10 times higher. What that will have as an impact on the optimization techniques, on the optimization, and we then also let it run for, of course, CNC milling and 3D printing, but the settings are rather similar. So we don't want to have a benefit in resolution level. So for the CNC milling tool, the CNC milling tool was equally thick as the minimal structure width here, and for 3D printing, identical. So the printing resolution of my machine was set to the same resolution level as the die casting structures. All right. So once all of the input has been given to ColdStream, you can then submit the case. And once the case is ready, you can then have a look at the performance, or what ColdStream did. Let's first have a look at the die casting results with this small release angle, so with the 2 degree release angle. And if we then have a look at, yes, I will color this slightly differently. Yes. So everything in green here are the structures that are being formed within the design domain. So everything that is solid or aluminum. And if we then have perhaps also plot the streamlines and make this a bit more clear. Yes. We can then have a look at what design philosophy ColdStream went with. So the inlet is here on the left, and then ColdStream adds two big channels or two big structures to split the flow to the sides and through the middle. And then when it moves closer to the end, or when it moves further downstream, these structures help, first of all, to help conduct the heat from the heat sources to the coolant, as well as help conduct or help guide the flow throughout the outlets. As you can see in the outlet, there are again big structures to funnel the coolant towards the outlet. So yeah, this is the structures that are being formed with die casting with a small release angle. We can then have a look to the ones with the bigger release angle, where of course, we'll quickly, yes, the design philosophy is now completely different. So now with a big release angle, ColdStream didn't have enough space anymore to put more structures, so it can only generate something like this, where you have a big blocker, where you have a lot of vorticity, or a lot of vorticity, which is very good to cool down, and then it further, and then the coolant further goes down towards the outlet with some additional cooling structures towards the end. So the design settings very much affect, of course, what ColdStream will do. We can then have a look at the CNC mill design. So I will make this a bit more visible again and put the streamlines on as well. Yes. So with the CNC mill design, where ColdStream will only consider one axis CNC milling, the design philosophy is rather similar again to the die casting with a small release angle. No, it's the other way around. Yes. So at the inlet, or towards the inlet, it will put two big structures again to split the flow towards the sides and the middle. And then the structures further down are smaller to help with the cooling, as well as with the direction of putting the directing the flow towards the outlet. And then the most interesting region, or the most interesting case, is of course the 3D printed design. Yes, where ColdStream has the most freedom to do whatever it wants. If we solely look at this, it's not immediately clear what ColdStream did. For that, we'll have to have a look at the negative, so the remaining fluid, and it becomes immediately clear what ColdStream did. So again, similar to the CNC and the die casting, it put quite big structures in the middle to split the flow in the middle, towards the middle and over the sides. And further down, it's all more cooling channels interwoven to help cool down the both heat sources. So this is, of course, very intricate and very interesting looking, in my own opinion, which is only available with 3D printing. The most important question then is how do those results compare to one another? For that, I put all the key performance data together in a comparison view, where we of course are mainly interested in the temperatures and the pressure drop. So in the first table, we'll see the maximum, mean, and minimum temperatures of the die casted with small release angle, and then with the die casting with a big release angle. Then we have the CNC milling, and last we have the 3D printing. If you have a look at the heat sources 1 and 2, we said for 3D printing, the maximum temperatures of those heat sources are 51.5 degrees Celsius. So a 6.5 degree heat up compared to our 45 degree inlet temperature. While for CNC milling and for the die casting with the small release angles, those maximum temperatures are 52.5, 52.6. So a 7.6 degree heat up compared to our 45 degree inlet temperature. So by using 3D printing, the more expensive optimization technique of the two, the most expensive manufacturing technique, of the two, you will get a design that performs, in this case, with these inputs, 15% better compared to more conventional die-casted and CNC milled designs. And then, yeah, lastly, we have the die casting with the brick release angle. Of course, those temperatures are much higher because, yeah, ColdStream couldn't do that much. So that's the manufacturing settings were the main constraints in that optimization technique. Looking at the pressure drops, it's all below 400 Pascal and all pretty much similar. So no improvements there. All right. So yeah, now coming back to the cost question. Do you want to consider 3D printing compared to die casting or CNC milling? That very much depends on what you can get out of it. For some people, or for some industries, sorry, getting a 15% improvement in temperature-wise is worth the cost, or is worth the benefit of increased manufacturing costs. While for other industries, like for instance, if you have people like you and me to buy stuff off the shelf or online on Amazon, for instance, it might be more beneficial to have a lower performing design at a reduced manufacturing costs. So it's a bit of a trade-off what you want to do, but I urge everyone who has access to generative design software to at least try with 3D printing and see what the benefit is, what ColdStream can return. As a small side note, we optimized a commercial CPU cooler quite recently, where there we found a 55% improvement in thermal performance. So yeah, there's of course out of the question that 3D printing is much better compared to skiving in that example. All right, looking at the time, and I see that we are running out. So unfortunately, I don't have time to cover any Q&As or to cover any questions in more detail. But I want to leave off with these final notes. By using generative design software like ColdStream, can very much reduce the design cycle time from 2 to 6 months in classical engineering to just a couple of weeks. The designs themselves, especially with 3D printing, can be beyond human capabilities, and the human input is very much reduced from 10 to 20 days of manual input to less than an hour. It's preparing the CAD file and filling in the relevant information on ColdStream, and the second part just takes a couple of minutes. With ColdStream, anyone can use it. It's not that complicated to work with it. It runs on our subcomputers, so you don't have to invest in that. And it's cloud-based, so no local installation is required. It's always up to date with the latest version, and you can access it from whatever browser you would like. All right. You can get access to ColdStream of your own by following this link. It's available via our website. And if you all are considering a full license, you can of course contact us directly by emailing to this email address or by calling this phone number. All right. We're very close to the 30-minute mark. So thank you all very much for your attention, and I hope to see you in the near future. Bye bye.